Hey guys, this is video 12.3. We're going to be taking what we've learned about the acid and base basics, and we're going to start applying it with a new definition. So we're going to jump to page 9. Okay. So we talked in the last couple of videos about Arrhenius acids and Arrhenius bases. Remember, Arrhenius acids produce the H3O plus ion in solution, and bases produce hydroxide. So this is another definition of acids and bases, ones that I would again encourage you guys to make flashcards for so that you have and you can keep track of all the different definitions. Bronsted-Lowry acids and bases, okay? And a Bronsted-Lowry acid, by definition, is a molecular ion that is a proton donor, okay? So if we talk about proton, this is what a proton is going to look like in an equation. So as a review, this is going way back to like Unit 2. If we were to count our protons and our neutrons and our electrons, okay, for this species, this ion, all right, well, let's take a look. Well, H, it's got one proton. If you look at the mass of hydrogen, right, it's 1, but we got to subtract out the proton number, so we have no neutrons. And now with a plus charge, we originally had 1 electron, but a plus means you subtract it, so we are left with just a proton. So H plus, whenever you see that ion written in a formula, there you have a proton. Okay, so keep that in mind. That's something big. Maybe you want to make a flashcard with that says proton on one side and H plus ion on the other. Okay. And on the flip side, a Bronsted base is a substance that is a proton acceptor. Okay, again, it's going to accept one of those guys. So really what's happening here with acids is that the acid, when you look at the reactants to the products, the reactant is going to have one more H, and the product is going to have one less because it lost it. It donated it. It gave it away. Where on the flip side, a base is going to have a smaller number of H's, and then it's going to increase its number of H by 1 when you look at the products. And that's really what this term conjugate means, guys. It's kind of like opposite or becomes. Okay? Okay, it's kind of like opposite is the way I think of it. You can look up a more technical definition if you want to, but I just kind of think, okay, opposite. So an acid becomes a conjugate base. A base becomes a conjugate acid. So you're only going to ever see this term conjugate on the product side. Okay? So if we take a look here at this example, hydrochloric acid, HCl. So the first thing you're going to want to do is kind of pair up the pieces that look alike. So if you split up your reaction, reactants, and products, so I'm going to draw a bracket from HCl to Cl because their formulas are pretty much the same, and then H2O to H3O. So those are kind of the pairs here. So you're going to have to identify conjugate pairs within this. So let's take a look here, figure out which is the acid and which one's the base. So HCl, if I take a look, there's HCl, so one H and one Cl. When I look at it, the species that it becomes on the product side, notice how the number of H's did what? It decreased. So HCl has donated or given away a proton and become a base. So that's how I know that, hey, this is my acid because it lost a proton. Okay, got rid of that H, and the charge went down or decreased by 1. So here it was 0, here it's -1. So not only is it giving away an H, but its charge is also decreasing. Okay, so if I start with an acid, the species it becomes is that conjugate base. That's that term opposite, okay? If it started as one species, it's going to become the other, the opposite, the base. And notice how it's a conjugate because it became a base, all right? Well, if HCl is my acid, then what does that mean? I'm sorry, I'm just trying to make this clearer for you guys. If this was the acid, then what does H2O have to be? Well, by definition, a Bronsted base is a substance that is a proton acceptor. So we have 2 hydrogens here on the left, and now we have 3. So it brought in, it accepted that proton. The acid gave the proton away so that it went to the water. So that, by definition, makes it a base. And what do you think that base is going to become? Well, if it was a base here, it's going to become the conjugate acid. So this is the process you're going to have to go through. You're going to have to label all the different pieces, okay? Now, and you're going to have a quiz on this, and the vocab is going to be with it as well. But this is one thing that people either get hundreds on or they get 50s because they kind of mix up the pieces. They're good at matching up the pairs, but trying to identify it. So this is where it comes to definitions. You've got to know that an acid is a proton donor, so its H is going to decrease by 1. Its charge is going to go down by 1. So let me just write that in. Lose H, charge down 1, where a base is going to gain an H, and it's going to, and the charge increases by 1. Okay? So we want to sum this up, guys. Bronsted acids have a conjugate base formed from the acid losing a proton. That's kind of what I just summarized. Where on the flip side, if we said a Bronsted base, they have a conjugate acid formed from the base gaining a proton. All right, and this is kind of showing it, right? The H from the acid here goes over and joins the H from the bases, so that means Cl became my conjugate base, and H2O became H3O, which became my conjugate acid. Okay. Now, a lot of times with acid-base reactions, guys, they're actually reversible, so you can go backwards and forward. Now, if we take a look, and this is where it gets confusing. If you get confused, ask questions in class. If we take a look and we were to rewrite this, you do not have to write this down, okay? So if I had H3O plus Cl minus, and it produced HCl plus H2O, well, let's take a look, okay? These two guys are going to go together. These two guys are going to go together. Well, what's happening with my H3O plus? Oh, it lost an H, therefore I know that's my acid, which means this has to be the base. Okay, and this HCl then becomes my conjugate. So it goes backwards and forward that, hey, those species still stay as an acid or a base. Conjugate, again, just means it's on the product side. So you're only going to see that term conjugate on the product side of your reaction. So let's kind of do this together, these two, and then I'm going to have you guys work the practice problems on your own or try. If you feel confident with this right now, pause the video and then go through and label these all on your own as well. Okay? So the first step I want to encourage you guys to do is to draw the brackets, okay? Kind of match up the species that look similar. So I see NO3 here, and I see NO3 there. That means these two guys are going to go together. And then H2O and H3O. So again, think, definitions. What happened? I don't care which one you start with. I'm going to start with H2O because it's the first one I see. I have two H's. Now over here on the right, it becomes three H's. So which one by definition is an acceptor? That would be our base, okay? That would be the base. So once you find one piece, the rest kind of all fall together. So if H2O is the base, that means the species it becomes is going to be the opposite, meaning conjugate acid. If H2O is the base, then HNO3 has to be my acid, but let's kind of look deeper. My H's, I had one H here, I have no H's there. That means I donated or gave away an H, therefore that's by definition an acid. NO3 or nitrate is going to become my conjugate base. Okay, so this is one thing. It may click for you after 2 or 3 problems. It may take you 10 or 15, okay? So don't give up. Keep working through it. But again, it goes back to knowing your definitions. You've got to know the definitions, guys. So again, if you feel confident now, pause the video, move on, try to do all the rest on your own. I'm going to keep working through them and explaining them. Okay, so NH3, I'm going to pair that up with NH4. H2O is going to be like OH minus. Remember, guys, H2O, if we wrote it as HOH, that can make it a little bit easier to see which one it kind of goes and pairs with. So again, let's start with NH3 because it's the first one I see. Number of H's was 3 here. It became 4. So it gained a hydrogen. It gained a proton. The charge went up. It means it's my base. Okay, if I look at H2O, H2O had 2 H's here. Oh, now it only has 1 over here, so it lost or gave an H away. Oh, that's going to be my acid. The opposite of my base. We paired those up. That means this is going to be my conjugate acid, and this is going to be my conjugate base. All right? So keep working through. I'm going to kind of go a little bit quicker with these problems. go through that process every single time. Just like net ionic equations, it's a process. If you try to skip steps or think through them, in a weird way, you may get a little confused. But go back to your definitions, okay? It's crucial. I cannot stress it enough to know your definitions of the acids and bases, okay? So, pair them up. This is actually the same one we just did. Didn't even realize that. So, base, acid, conjugate base. Wow, I need to change that. All right, HCl can pair up here. Water is going to pair up there. I need to change some of these examples. I didn't even realize it. So, lost in HCl, lost in H. That's my acid. HOH gained in H because it went from 2 H's, 1, 2, 2, 3. That's my base, conjugate acid. Okay. So, again, pause it, try these. I'm going to keep working through them. Pair them up first. Again, if you can visualize it with your eyes, guys, after 5 or 6 problems, great. If you need to draw the brackets, draw the brackets. Okay, it doesn't hurt anything to do that. HI, lost in H, it's an acid. HOH, 1, 2, became 3, so it gained in H. Base, conjugate acid, conjugate base. If I'm going too fast, pause the video. Call me over if you're confused. All right? The more you do, the easier this will get. HNO3, there's that, acid, base, conjugate acid, conjugate base. Now, with these two examples, did you notice water? Water was in both of them. Okay? So I'm going to kind of box this here, box that there. Okay. And I want to look back at this one specifically too. Notice how water, guys, is in a lot of these because, again, aqueous solutions, okay, makes sense. But notice here in these two examples it was a base, but in this one back here on page 9 it was an acid. Okay. That's what we call an amphoteric substance. Okay. An amphoteric substance. So by definition, guys, amphoteric means substance that can act like an acid or a base. And the biggest example that you're going to see, guys, is water. Now, it doesn't mean it's strong, doesn't mean it's mostly probably a lot of times going to be weak, okay, because it's that first ion that gets removed that has it, that has the strength. But water, guys, is very weak. But it's got 2 waters, it's got 2 hydrogens, so it could go either way. It could become H3O plus, like we've seen here when it's a base, or it could become OH minus when it loses one. Okay, but the big thing with amphoteric substances is they must have at least one hydrogen in their formula. Okay, at least one. So it's got to be able to take one in or lose one. So a lot of times, guys, one has got to have at least one hydrogen. So if we look at this example right here, which one's amphoteric? Which one could we eliminate right away? D, because it doesn't have a hydrogen at all. Okay. Now, the other piece that you've got to think about is it needs to be able to take one in. Not only give one away, but it's got to be able to take a hydrogen, or a proton, I should say. It's going to be able to take a proton in. So think about what the charge of the substance is that's next to it. Okay, if we were to split these all up. SO4 is a 2-. This one's already full because there's 2 hydrogens there. This one can't be amphoteric because it can't bring in any more hydrogens, okay, any more protons. Same thing with HBr because Br is a -1, so it's full. C is going to be the correct answer. Why? Because look, there's a negative charge here. We could bring in another proton to this guy and it could become H2SO3. We could also lose a proton and become SO3 2-. Okay, so the thing you want to look for is, hey, 1, it's got to have at least one hydrogen. 2, then start looking for like a negative charge to kind of think, hey, it could be that base to be that proton acceptor. Okay, so at this point, go ahead and do practice 2, kind of work through the pairs practice with this where you're answering some questions. And then, oh wow, I didn't even see that got messed up. Sorry, guys, number 5 is right here. And then labeling all the species with that as well. All right, until next time, I'll see you later.